Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day, here in my virtual classroom. Step one inside as we jump into section 7.5 in the Big Ideas Math Integrated Math 3 textbook, where we are using recursive rules with sequences. What's it called? Using recursive rules with sequences. That's what it's called. Perfect. I just want to make sure that's what it was called. And by the way, we're going to have 70 problems on this one, by the way. And by the way, this is the last section of the chapter. And by the way, I'm doing recordings in IM3 with IM1 kind of not simultaneously, but I just did a recursive rules one with IM1 not too long ago. So this might feel a little repetitive for me. I apologize if I feel like I kind of speed rushed through it going like, I just taught you guys this, even though you would have learned this in IM1 a couple years ago, but it would have been something you would have learned. So I am curious to see, and there are 70 problems. I'm curious to see how they try to expand off of this stuff, but recursive rules with arithmetic and geometric sequences had been covered in IM1. So we'll see how this looks in IM3, guys. Jump to the description section down below to find the PDF of those 70 problems, along with the lecture portion, along with timestamps to every single thing we have, along with graph paper if need be. Without further ado, I'm going to go ahead and get started. We're going to evaluate recursive rules for sequences, write recursive rules for sequences, translate between recursive and explicit rules, and use recursive rules to solve real-life problems. I don't remember the bullet points that I had in IM1 with this stuff, but so far none of this seems different. They'll ask different kinds of questions probably, especially for the word problems. But yeah, if there's one thing that I do remember, it's that I've been saying that phrase explicit rule a whole bunch, even for you guys. And it's now introduced here. And I do believe that in IM1 they did the same thing. They didn't say the phrase explicit rule specifically until this one to say, hey, the thing we've been doing each time to find the nth term of whatever, we've been using what are called explicit rules. So they really should have said this one earlier here. Recursive rule is a different kind of thing where you're finding the next term. The way that we write the rule at least will be different. So far in this chapter, you've worked with why don't I just let them say it? So far in this chapter, you've worked with explicit rules for the nth term of a sequence, such as a sub n equals 3n minus 2, and a sub n equals 7 times 0.5 to the n power. An explicit rule gives a sub n as a function of the term's position n in the sequence, meaning you substitute that value to find its position. 100th term, plug 100 into the equation, like that. Recursive rules, not quite the same. In this section, you will learn another way to define a sequence by a recursive rule. A recursive rule gives you the beginning terms of a sequence and a recursive equation to tell how a sub n is related to one or more preceding terms. The most common type of thing you'll do is to find the next term, take the previous term and do something with it. And then take that previous term and do something with it. It's actually the way that we tend to describe rules as a whole. You'll see what I mean when I show you an actual pattern. But first, you're going to see the complex look of the rules themselves. Example 1, write the first 6 terms of each sequence. Now this one shows you that the 0th term is 1, which normally we say the first term, but oh well, a sub 0. A sub 0 is 1, and to find the value of any nth term, take a sub n minus 1, the value of the term before it, and add 4 to it. So if your 0th term is 1, I guess they're calling this your first term still. If your 0th term is 1, your a sub 1, first term, you take the 0th term and add 4 to it. You do 1 plus 4 to get 5. The second term takes the first term plus 4. 5 plus 4 is 9. You're literally adding 4 from one term to the next. You can see that as a list, and most people would understand and explain it that way. In other words, to find a sub 6, you're going to say 21 plus 4. A sub 7, 25 plus 4. And you keep going, and that's common for us. But the equation looks a little bit bizarro. And I agree. I understand. It looks different, but it explains what you do. The next one uses function notation. The value of the first term is 1. That's f of 1. Is 1. And the value of the next term, you take the previous term and multiply it by 3. So if the first term is 1, the second term will be 3 times the first term. 3 times 1 is 3. 3 times the next term, 3 is 9. 3 times 9 is 27, etc. Multiply by 3 each time. So you have an arithmetic sequence here with a common difference of 4, a geometric sequence here with a common ratio of 3, and they show you the value of the first term, starting from 1 apparently, on each of these. Okay. Writing recursive rules. In part A of example 1, the differences of consecutive terms of the sequences are constant, so the sequence is arithmetic. This plus 4, common difference was arithmetic. In part B, the ratios were constant, so the sequence is geometric. Multiply by 3 each time, makes it geometric. By the way, I'm more than expecting us to not only do arithmetic and geometric sequences for these. That's where recursive rules can get special. In general, rules for arithmetic and geometric sequences can be written recursively as follows. Take the previous term, add a common difference, or take the previous term and multiply a common ratio. If you noticed in the rules that they wrote, they don't just say, hey, add 4 each time. They also tell you where to start from. Because if I just said, hey, guys, add 4 each time, go. Most people will say 4, 8, 12, whatever. And I say, nah, that wasn't the rule that I was thinking of. Do it again. 0, 4, 8, 12. Nah, I wasn't thinking of that. Where should I start from? Start from 1. Oh, 1, 5, 9. Yes, that's right. So you have to tell them where to start from as well. That's not mentioned here. When we see the examples, you are going to see. That's what we do. So here's an example, and here's a rule. And if I asked anyone with any math knowledge on what this rule is doing, everyone would say add 10. That's cool. That is the common difference. But you also have to state where you're starting from. And in this case, we have to write it as an equation bit. Now, we are adding 10 each time. That is very true. And we are starting from 3. So those are the two things to note. Common difference, first term. Not unlike explicit rules, which is how we're going to be able to do conversions from one to the other. Now, how do you write it? You do it like that. You take the value of the next term is the value of the term before it plus 10. So we'll write it like that. A sub n equals a sub n minus 1 plus 10. And, oh, by the way, the first term is 3. So you have to kind of let them know where to start from, right? Otherwise, it doesn't work out. Now, the second chain right here, I don't know if you can tell what's going on so far. I can't. I have to look into it. It looks like it looks like a common ratio. I think we're multiplying by 5 halves. Someone would figure it out from here as 2.5. I think you're multiplying by 5 halves each time times 2.5. Do 1 divided by the one before it. Let's see. They say it is 5 halves. So it's a geometric sequence. You're multiplying by 5 halves each time. Your first term is 16. So what do you say? Take the previous term times 5 halves to get the next term. It's going to look like that. 5 halves times the previous term. So that's what that means, right? A sub n is the value of the nth term. A sub n minus 1 is the value of the n minus first term. Whatever n is, subtract 1 from it to get the value of the previous term. So that's why we're multiplying by 5 halves. And, oh, by the way, a sub 1 is 16. So that's the whole answer there. Writing recursive rules for these sequences. Now, these are special cases. If you know this one, this is a classic Fibonacci sequence. They actually say that right here. This is the Fibonacci sequence. The Fibonacci sequence is not a common difference nor a common ratio, but it is a recursive rule. You use previous terms to get the next term specifically. And I think this is, listen, these are things I actually spoke of in the IM1 video at the time. So I think this is the way I did it, something like this. These two terms add to become this term. So 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 would give you the next one, 8, and so on. So in the Fibonacci sequence, that's what you're doing. Now, how do you write that rule? Well, what you have to do is look 2 terms ahead, right? We have to get this term from the previous 2 terms, which means we not only need to show those in the equation, the value of this next term is the value of the previous 2 terms added together, but you also have to mention what the first 2 terms are. So here's how they're going to say it. The first term is 1. The second term is 1. And the value of any term takes the value of the 2 previous terms added together. The value of 2 terms before plus the value of 1 term before. Let's see if they show a test. They do. Oh, that's part B. So a test of that, for example, we can tell that 1, 2, 3, 4, 5. A sub 6 would be A sub 4 plus A sub 5. Now we know that A sub 4, the value of the 4th term is 3, plus the value of the 5th term is 5, which is 8. Right? So that's how you use that formula to write the thing out. We can do it in our own set, but that's how we show it. I didn't see the second one yet. 1, 1, 2, 6, 24. I don't want to look down below. I'm trying to guess what it is on my own. Well, 1 times 2, 1. This can come from 1 times 2. This can come 2 times 3. This can come 3 times 4. What I need to figure out is where those numbers are brought from, though. Oh, 2 divided by 1 but that one number, 1 times 1 plus 1? No, that doesn't work. Okay, I can see where the numbers come from, and this would have then been these, do you use the value of the term? I don't know where these come from, but this is, oh, that's not 3 times 4. That's 6 times 4. I'm trying to think of where these come from. I can't tell. Let's see. I actually don't know. The terms neither have a common difference nor a common ratio. Denote the first term to the one. 1 times a sub 0, 2 is 2 times a sub 1. Oh, okay. You know what? I was thinking of that. So what they're doing, they're actually literally, they're literally using the term, okay. I didn't know you could do that, and you could. I didn't know if this is a special case. I was going to say if I could take the term position themselves, and I could get it from that, because I was thinking I could do the previous term times 3 and the previous term times 4. I said, this is 6 times 4, and there's a 6. Where does the 4 come from? It's kind of a fourth term kind of deal. So what they're doing is they're increasing this number, this 1, this 2, this 3, this 4, is just an increase of just that number itself based on the term you're looking for. So the fourth term, how do I say this? The fourth term is, I guess this is the 0th term is what they're saying. And this is the first term, second term, third term, fourth term. So the fourth term is 4 times the previous term's value. Okay, that one's different. It's interesting. These are special cases, and that's recursive one. Sorry, I'm looking at this as we go organically. So if we get questions like that, now I'm in the know of what kinds of things we can look out for, which is pretty much anything. And I'm intent on doing that. All right, translating between recursive and explicit rules. I'm going to say it's straight up from here. Identify what kind of sequence thing it is, arithmetic or geometric. Know the equations for those rules. And show where your first term and common difference are, or first term and common ratio are, because both rules use those values. In this one here, this is an explicit rule, but you need to find your first term still, because this is a simplified explicit rule. So you got to substitute 1 in the equation, get your first term of 2. Your common difference is 8. If you notice the value that's multiplied by your number of terms, that'll be your common difference, 8. So first term is 2, common difference is 8. When you write your recursive rule, you say it like that. Your first term is 2. And then your next term takes the previous term plus 8. So you don't have to get the in-between of actually coming up with what the terms are to do it. You can translate from one to the other as long as you're straight there. This one is straight up the explicit rule for geometric in such a way that this is your first term and this is your common ratio. So we can place those in exactly as we want to as well. A sub 1 should be negative 3, and a sub n should be 1/2 times a sub n minus 1. Where is it? Right here. Here it is. A sub 1 is negative 3, and a sub n is 1/2 of a sub n minus 1. Translating from recursive to explicit, same deal. You have the first term literally spelled out for you. You can use that in your formula, and here's your common difference in an arithmetic. So you can write the rules we know how. First term plus common difference times n minus 1, and they go to their distribution path like that. So they, in simplification, I should say. So they end up writing it like this. That's for an arithmetic. Geometric. First term right here, common ratio is 2. So 10 times 2 to the n minus 1 power. We're going to have the a sub 1 times r to the n minus 1 power like that. Once again, I need to state this. Outside of that really one special, because we spoke Fibonacci sequences, out of that one special case with that n thing, so far everything I've seen was covered in IM1 material, in the actual section on that stuff. Solving real-life problems, maybe this will get a little more complex. We'll see. A lake initially contains 5,200 fish. Each year, the population declines 30% due to fishing and other causes. This is just depressing. Every single time I see something in population of like wildlife, it always declines. I wish that they would increase time to time. Due to, although they're delicious, due to fishing and other causes, so the lake is restocked with 400 fish. Oh, there you go. It's restocked. Now, I'll tell you what, that's a new thing for me when it comes to, not for me personally, but at least for IM1. IM1 wouldn't have said the restock portion. They would just say the decline and write the thing for that. But with this restocking, how will this come into play? Let's see. Write a recursive rule for the number a sub n of fish at the start of the nth year. So each year, they lose 30% of what they had, but then they add 400 fish on top of it. So I have an idea of what I would do. They're probably going to do the same thing. This is a constant on a per year basis, and this is the percentage decrease. So write a recursive rule part A. Now, recursive rule, that's the section. So you take 30% decrease is 70% of, that's a subtraction. They're showing that right here. 70% of the previous amount that you had, and then they add 400 in addition to it. So it's neither arithmetic nor geometric. It's kind of a combination of both, right? So you have this common ratio bit, but plus adding 400 each time to what there is. And by the way, you start with your first initial amount of 5,200. I don't remember it saying that. Oh, it did. That's the first thing it said. So you start with 5,200 and then you do all that from there. Part B. Find the number of fish at the start of the 5th year. Now, The thing about the recursive rule aspect that I want to say is I couldn't think of an explicit rule to write for you on that one. I mean, maybe it's very simple, but the idea is 400 needs to add to make the new amount, and then you need to take that percentage of that. So I don't know if I'd really come up with a good set of doing that. So recursive is really the only way to go. So what do? You got to work that out each time. 0.7 times the previous answer plus 400. And that previous answer bit is something that your calculator would legit do for you. Like you have to, here, let me go to my calculator for example. If I have, the number 5 as an answer, I can recall a previous answer. If I want to do 2 times the previous answer, I do second and then this minus button, and it recalls the previous answer was 5 and plus 4. What's 2 times 5 plus 4? 14. Right, so you can recall a previous answer that way. I can do it right here as well. Minus 6. Minus 6. It'll recall the previous answer if I use an operation from that straight up. I like when calculators are able to do that for me. Anyway, so we're going to have to do that recursively several times. We're in the first year, so we'll have to do it 4 more times. And ultimately, when you do it, this is how many are here after by year 2, and year 3, and year 4, and year 5. So about 2,262 fish. 2,262 fish at the start of the 5th year. Part C, describe what happens to the population of fish over time. Well, it does decrease, but it's decreasing by a lesser amount each time. Oh, they're really showing what happens over time here. Eventually, it seems to converge at the number 1333. I guess what's happening is because you're taking 70% of 1333, which must be about 400 of a decrease, and then you're adding 400 back. And then take away the 400 and add 400 back. So that must be what's going on here. So let's see how they say it. To describe keep pressing. Oh, and here's another thing. Yeah, you can keep pressing enter on the previous thing to recalculate this over time. What's cool is it'll take the previous answer of what you literally had and do that to it. So I can keep pressing enter until it does it. So it sounds like they're really making you work on the calculator. You can also do this thing on spreadsheets. It actually just copy paste and you'll get it there. But 1333 just shows that that's what it's declining to. Over time, the population of the fish in the lake stabilizes at about 1333 fish. And I'm covering a graph that shows that convergence for that thing here. So it's an arithmetic geometric yexes like that. All right. I'm as invigorated with this lecture. I'm probably much more invigorated by this lecture than you are, but that was an interesting problem. All right. Here's another example 7. We have 70 problems to do, so you can tell they're going to do a lot with them. You borrow $150,000 at 6% annual interest compounded monthly for 30 years. The monthly payment is $899.33. So this is compounded monthly. That means we'll have to do that divided by 12 thing. I got to think about... So I think our rule is going to be on a monthly basis. That way we can, if it's a payment, we're subtracting it. So I guess we'll have to take this away each time as we borrow this interest. Okay, I'm going to look at their equation, see what they do, and do it. Find the balance after the third payment. Due to rounding in the calculations, the last payment is often different from the original payment. Find the amount of the last payment. Okay, let's see. Understand the problem. You're given the conditions of a loan. You're asked to find the balance after the third payment. Yes. Make a plan. Because the balance depends on the balance after the previous payment, write a recursive rule. Yes. Then use a spreadsheet. Oh, they actually say use a spreadsheet. Use a spreadsheet to find the balance after each payment rounded to the nearest cent. You could also use the calculator, but okay. The monthly interest rate is 0.5% because 6% divided by 12 months there. So that's a monthly interest rate. So we increase by that much each month. So this is a monthly balance because we're going to make a payment every month. So every month you're increasing 5% of that balance, but you got to also pay $899.33. So here's that interest, and then boom, 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 boom. Use a spreadsheet and the recursive rule to find the balance after the third payment and after the 359th payment. Now they're using some code here. I actually didn't even know you could use the function round. I do something else on these generally, but yeah, you can use the function round. They do a rounding here. We might have to follow this for some problems. If so, I'm going to have to pause my thing, go to a Google Sheets thing and pop it up. But this is where you can round to 2 decimal places. They say do the calculation, round to 2 decimal places. This B2 says take this column right here, or this cell right here, and then apply that thing. It's like to the previous answer. And you can kind of copy, paste, drag, and drop and do this here. And they show what happens here. They say for 30 years, so we'd have to do it for 360 months total and figure out what's going on. Now, they said the balance after the third payment is this much. I was looking at that 4, but this is the 3. After the third payment is this much. The balance after the 359th payment is this, so the final payment is that. What do they say about the whole rounding thing? By continuing the spreadsheet for the 360th payment by using the original monthly, the balance is negative 391. Oh. This shows an overpayment of 391, so it's reasonable the last payment is 895.42. I'm gonna have to look into what that whole thing is saying at the very end. As far as what it is, I mean, I get it because we're subtracting the thing that we would have paid versus that minus thing there, so we're gonna have to pay a little bit more. It's just interesting on what they asked versus what we answered. They said the last payment is often different from the original payment, so I guess that's because, okay, now I get it. They're saying that you won't go exactly to 0 on that last payment. You're going to owe a little bit more. So there it is. See, I'm not in finances. I'm bad at finances. Do not seek me for, you can seek me for stock advice, but not for other finance advice at all. Don't seek me for any of it, actually. All right, guys, numbers 1 and 2, vocabulary and core concept check. Here we go. Complete the sentence. A recursive blank tells how the nth term of a sequence is related to one or more preceding terms. I assume I can use the word rule, a recursive rule. That's what I'd be saying now. Number 2, writing, explain the difference between an explicit rule and a recursive rule for a sequence. Well, this tells you the recursive thing here. This might be recursive function, recursive equation, I don't know. But an explicit rule is where you can find the value of any given term. Explicit, a word I've been saying this entire chapter. Find the value of any given term. And recursive, let's see. Recursive, find the value of a term based on preceding terms. Preceding term or terms. Normally, especially for arithmetic and geometric, it's based off the previous term. But for Fibonacci or some special case ones, it can really be anything. It can be from 2 terms ago or something like that. All right, guys, I have numbers 3 through 70. I'm kind of dreading it. We'll see where we go from here. Good luck to us. Here we go. The thing that I'm dreading with it mostly is because I kind of just came off, not literally just came off, but pretty recently came off doing a recursive thing. And outside of those word problems, I'm not really seeing too much of a difference between what IM1 was doing and what IM3 is doing. So welcome back to some IM1 stuff, I guess. In exercises 3 through 10, write the first 6 terms of the sequence, where the first term is 1, and the next term we can find takes the previous term plus 3. Now, this is what, again, brings me back to what I did at the time for IM1 stuff. I'll start slowly with this one to show you how this equation idea is going on, but after that, I'm probably going to speed up pretty quickly. So the first term is 1, yeah. The second term takes the previous term, a sub 2 minus 1, so a sub 1, and adds 3 to it. A sub 1 is 1, and 1 plus 3 is 4. The third term takes the second term plus 3. The second term is 4, and 4 plus 3 gives you 7. The fourth term takes the third term plus 3, which is 7 plus 3, which gives you 10. I said go slowly. I'm writing quickly, but this process is not the way we have to go about doing the problem. Take the fourth term plus 3 for the fifth term, which is 10 plus 3, which is 13. And the sixth term is the fifth term plus 3, which is 13 plus 3, which is 16. So the 6 terms of the sequence are 1, 4, 7, 10, 13, and 16. That is the full workload, and that explains why this equation does what it does. Right? Now, for this problem, I'm not going to go quite as slowly when it comes to the workload that I write. If the first term is 1 and your next term takes your previous term minus 5, this time I'll just say a sub 1 being 1. A sub 2 is the first term minus 5, which is negative 4. The third term is negative 4 minus 5, which is negative 9. The fourth term is negative 9 minus 5, which is negative 14. The fifth term is negative 14 minus 5, which is negative 19. And the sixth term is negative 19 minus 5, which is negative 24. So hopefully you're getting the gist on how this thing will come into play, at least when it comes to how the rule is written and why it's used the way that it is. From here, we can go significantly faster once you recognize that's your first term, that's your common difference, or that's your first term, that's your common ratio. And I intend on going faster, specifically for the IM3 crowd. Not only because you're kind of that higher level, but also this would have been something you would have done in IM1. I mean, do you remember it? Maybe. Were you actually taught it? Yeah, I don't know. But yeah, we still do it. All right, f of 0 equals 4. I do believe they're referring to that as your first term regardless. F of n is 2 times f of n minus 1. So what this means is, again, 2 times the previous term, just because they use function notation means no change in that otherwise. So f of 0 is 4. F of 1 is 4 times 2. Okay, so that'll be 8. F of 2 is 8 times 2. F of 3 is 16 times 2. F of 4 is 32 times 2. F of 5 is 64 times 2. Now, do I do f of 6? No, because this would have been the first term there of f of 0. So it's that multiplied by 2, excuse me, each time. Those are your first 6 terms of this geometric sequence. Given that it has a common ratio, that's what this looks like here. Number 6, and I think it's at this point that I'm really going to speed run it, meaning I won't even write the f ofs per se. I'll copy down the problem. F of 0 is 10, and f of n is 1/2 times f of n minus 1. Now we're taking half of what we had before, right? So here, I'll do it this way this time. I'll actually write them out and get them prepped. So we start with 10. Then we have to, again, multiply by 1/2. So you can see I'm kind of speeding up as we go. I'm showing a little less work over time since I don't have the f of n's, f of 1, f of 2, all that kind of stuff. But we're still taking half. And I want to show these 1/2s at least because the calculations. 5 times 1/2 is 5 halves. 5 halves times 1/2 is 5 fourths. 5 fourths times 1/2 is 5 eighths. 5 eighths times 1/2 is 5 sixteenths. Don't you dare go to that calculator for a problem like this. Just use fractions. You're totally good there. Or you could. I don't know. They said 1/2. If they have a fraction, I'm going to stick with the fraction. If they give me a decimal, I'll use a decimal. I'll use the calculator for that. Number 7. Now we're in a stage where it depends on the problem, where we might have to look into writing some work so we know where we're at. I didn't realize we were going to do special cases. I wanted to kind of go faster with these if they were different. You know what? We might have to write some of these things out. So we're squaring the previous term plus 1. So, yeah, a sub 2 is 2 squared plus 1. 4 plus 1 is 5. A sub 3 is 5 squared plus 1. Maybe I should write 5 squared plus 1. 5 squared plus 1, which is 26. Oh, I have to use the calculator on this. A sub 4 is 26 squared plus 1. Which is 677. And I think what I'm going to do here for the next 2 terms is this. I'll show you in the calculator. But 677 squared plus 1 equals. So right here, I can, in the calculator, I just did this last thing plus 1. So I can do the previous answer squared plus 1. And I'll hit enter twice, basically. Boom. Oh my goodness, that's a big number. I have to look into how I can write that officially because I want to get you an exact answer. I have another calculator at hand, so give me 1 second. I have another one that can actually spit out the numbers without doing that. That number squared plus 1. Okay, I'm going to copy and paste. You can't see what I got calculated, but I'm going to paste it into this other thing just so you have it. Okay, so over here I got this other number. That was that big number there. It is a trillions number, 210 billion, excuse me, billions number. Is that billions? I think it's billions. So that first number before that, though, was 458330. And so a sub 6, I'm not going to rewrite the terms in a list, by the way, for this one. 458330 squared plus 1 equals that guy. I'll handwrite it, though. 21006. All right, so those are your 6 terms, right? A sub 1 is there. And then a sub 2, a sub 3, a sub 4, a sub 5, a sub 6. Okay. That is number 7. Definitely using a calculator on that one. Number 8. A sub 1. So first term is 1, and then we're going to square our numbers and subtract 10. That gives me some these numbers will be smaller. How much? I don't know. So here's where you kind of got to be careful with things regardless. I mean, you can use the calculator as much as you want here. Maybe I can let the calculator do the job for me, if that makes sense. So like, I don't know. I don't know if at this point they wanted you to use the calculator yet, but the first term is 1. Second term is the previous term minus 10. 1 minus 10 is negative 9. Now with this one here, we're going to be squaring negative 9. It will turn positive. Oh, these are going to get big. Never mind. Never mind. Negative 9 squared is 81. Minus 10 is 71. Positive. Positive 71. And then you square 71 and subtract 10 from that. So I'm going to jump to the calculator for these immediately, sort of. So we have, let's just do 71 squared minus 10. And the previous answer squared minus, whoops, that's a negative, minus 10. Oh, I forgot it's going to get big again. I might have to use the other calculator for this again. Shoot. So 5, oh, sorry, I'm going to write these numbers down. A sub 5 is 253109151, and A sub 6 equals. So let me use the other calculator for this guy. Give me one moment. Oh, I closed it. I'll let you see this other screen, though. All right, 253. Why do they even bother? They know your calculators can't do this. All right, this is a big number, guys. I wish I had this much money. It almost looks like I'm writing different numbers, like 640, comma, 644, comma. My bad, because these ones don't have commas here. Okay, so those are the 6 terms of that one. 1, then negative 9, then 71, and then it kind of just kind of looks weird, right, when you're doing them, but it's what they are. It's what we do. All right, number 9. Let's have smaller numbers, please, even calculator-free numbers. Number 9. Now, this is kind of one of those special case bits. I mean, I guess the other ones were as well, but they were quadratics. This one, though, we're going to use 2 terms to get the next term. It says the value of a term takes the value of the term right before minus the value of that next preceding term. So we have the first and second terms, essentially. The third term, f of 2, is going to take f of 1 minus f of 0, because this is f of 2 minus 1 and f of 2 minus 2. So f of 1 is 4, f of 0 is 2, and that's going to be 2. F of 3 will take the second term minus the first term. So that's going to take 2 minus, I think, 4, which is negative 2. F of 4 takes f of 3 minus f of 2, which is f of 3 minus f of 2, which is negative 4. And f of 5, I think this last one, f of 5 is f of 4 minus f of 3. So negative 4 minus negative 2, which is negative 2. I feel like these will somehow repeat themselves. It went 2, 4, 2, negative 2, negative 4, negative 2. Maybe it goes back up to 2 again. But I'm stopping there. Those are my 6 terms. So our terms are 2, 4, 2, negative 2, negative 4, negative 2. So it might go back to 2 after that. I don't really know. I kind of stopped keeping track. I think so, though. Number 10, we are multiplying the 2 previous terms. So 10, first term is 2, second term is 3. And then some other successive term takes the 2 previous terms multiplied. Doesn't really matter the order, but it seems like it's the term right before, etc. So f of 3 will be 3 times 2, which is 6. F of 4 will be 6 times 3, which is 18. F of 5 will be 18 times 6, which is 108. And f of 6 is 108 times 18, which is, I don't know. Oh, 44, 144, 1, wait, 1, 1, 8, darn it. 1, 1, 2, 2, 4. Wait, I'm going to say 1, 2, 2, 4. Let's see if that's right. 108 times 18. 1944. I was nowhere near it. Oh, 18. I did a multiplication wrong in my head. That's why I have the calculator. Okay, 1944. I tried. Darn it. Okay, 2, 3, 6. When you store one number wrong in your head, that's how to close my eyes and create the image and still screw up. 108 and 1944. But that's what we're doing, right? Multiplying one term by the one before it. Okay, guys. Numbers 11 to 22, write a recursive rule for the sequence. So now we have the sequence. We're trying to determine, is it arithmetic, geometric, special case, what have you. And then we're just saying what happens from one to the next. So this is an arithmetic sequence. We have a first term of 21 and a common difference of -7. Given that that is our common difference, this is how we're going to write the rule. The first term is 21, and the next term takes the previous term -7. That's literally all we kind of have to do in these. Once you recognize the ease of what to do specifically. Number 12, and I think I'm going to say most of these parts out loud that I am recognizing unless there's something special I have to do. This one here is a common difference of -11. Once again, subtracting, and once again, arithmetic. The first term is 54, and you're subtracting 11 from the previous term to get the next term. So -11, like so. So they can be pretty straightforward, and of course they can get difficult. We're going to see, I'm sure, both of those. Number 13. Looks like a geometric sequence this time, and it appears to be multiplying by 4. So with a common ratio of 4, we're multiplying 4 by the previous value, and we're starting from 3. So the first term is 3, and the next term takes 4 times the previous term as a general recursive rule. I'll take problems this speed all day. I'm good with that. Number 14. Number 14 would mark a fifth of the way done when I complete this one problem, after I complete it. Because we're going up to 70, baby. I'm going up to 70. At some point, your teacher assigns you some last problem, and you can leave without me. That's fine. I'll be fine. I'm good. All right. First term is 4. And any one term, we're multiplying by -3. You can have common ratios that are negative, of course. -3 times the previous term there. Special case time? Not quite. These are also geometric. You could see that you're dividing by 4 the first couple times, and you still are, but we don't mention what we're dividing by. We mention what we're multiplying by, and that might help you understand how to come up with those next terms in the fraction. Multiply by 1/4, the top stays the same. The bottom becomes 4 times bigger. That's how that works. So the common ratio is 1/4. First term is 44. So 1/4 the previous value. Number 16. We are adding 7. Starting from 1. Arithmetic sequence. Be darned. A sub 1 is 1. A sub n is the previous term plus, previous term plus 7. I don't have too much to state on these ones overall. I hope that you can pick up what they are. We've been practicing sequences the whole time. It's not like we don't know that part. But just the way that the formula works is like that. Okay. This one looking a little more special. And I think I see it for what it is already. Just sometimes it's nature of the problem. Generally, we're going to bank on some of the previous terms to make it happen. And maybe you can see this as well. We're multiplying for one. We're multiplying 2 with 5 to get 10. 5 with 10 to get 50. 10 with 50 to get 500. And apparently 50 with 500 to get the next value. So you're multiplying the next two terms to do this. So here's what you're going to need to do. Write out the first two terms because they're dependent on it. The first term is 2. The second term is 5. And any term after this, takes the two previous terms and multiplies them together. So the previous term right before and the term before that one. That way we can find the third term taking the second term and the first term and multiplying them. Number 18, expecting more of those. Literally, okay, I think this is the same thing. 3 times 5 is 15. 5 times 15 is 75. I'm going to only assume those two multiply to become 1125. Let me check. 15 times 75. Yeah, okay, so this is the same kind of problem, only two different first terms. Actually, only the first term is different. The second term is even literally the same. But oh, how different changing that 2 to a 3 changes everything else. It makes the numbers bigger, and then therefore you're multiplying by bigger numbers. That's how the recursion really takes hold. So it's going to be the same look of an answer of the previous problem, except that's a 3. But everything else recursively is the same. You're still multiplying the two previous values. So kind of weird. Wish they'd be a little more unique with it, but if you recognize a pattern. If you recognize it, hey. This next one looks like the sum of the two previous terms, just not the Fibonacci sequence specifically. And yes, there's something very special about the Fibonacci sequence specifically in nature, that it matters that we have it, or that it is that one. But 1 plus 4 is 5, 4 plus 5 is 9, 5 plus 9 is 14, etc. So your first term is 1, second term is 4, and then your next terms are taking the sums of the two previous terms there. Now, these are one of those ones where, this is a solution guide video, and generally I don't like to just give away answers like this. So it's more of, you might ask, how am I coming up with these? Sometimes it's a number sense thing. You got to be able to look at them. And hopefully you can see the same things as I am. Like, I'm saying them. I'm seeing them for the first time like you are. Just making number sense. But also, the book kind of foretells that we're going to have questions like these. So bank on a lot of recursion. We also even saw a different special kind of problem that we might run into a bump in a second and see what happens there. Excuse me. Like this one, for example, what I think, does this work? Yeah, what I think I'm seeing here, the numbers get smaller, so I'm starting to think subtraction. And boom, 16 minus 9 is 7, 9 minus 7 is 2, 7 minus 2 is 5. So this is a subtraction of 1 with the one before it. It's literally my first time looking at it, but that's just where my thought goes with it. My first thought would have been common difference, common ratio, stuff like that. But because we're in a sequence of these other kind of recursion ones, I'm not really thinking naturally anymore like that. So your first term, and you do need the first two terms to write some of these ones out because they bank off any two previous terms. So this one's, you have to be careful on how you write it. We are doing the first term minus the second term. So we have to do a sub n minus 2 because that'll be 2 before this term. And then minus a sub n minus 1. The last ones that we did were with multiplication and addition. Those are commutative, meaning I could have written the order either way. I can do this one like that or this one like that, and it doesn't change the result. For subtraction, it matters because 16 minus 9 is different than 9 minus 16. You feel? And of course, that would change the answer, and it would change how you do the rest of the subtractions. So it's important we say the one that's 2 terms before minus the one that's 1 term before gets you the value of, say, that third term. Number 21. The only thing I see in it, and it works, I was going to say I don't know, but I think I do now. We'll see how it officially flows. But this is 6 times 2. This is that number times 3. This is that number times 4. And that looks like that number times 5. So let's write those out. Let's still deduce what we have to say on it. This time I only really need the first term to write out what to do and then recursively work after that. So again, you could describe this rule just fine, but we have to write the equation. So the first term is 6. The next term, the second term is 6 times 2. The third term is 12 times 3. I should do this more specifically. The second term is 2 times the first term. The third term is 3 times the second term. The fourth term is 4 times the third term, etc. So to find the value of any term, what are we doing? We're taking n, the term position, times the value of the previous term. I was going to say, so there's recursion involved. All of these are recursive. So there's a bit of an explicit bit involved with that n on top of the recursion. It's an explicit recursive rule. And you do need to mention the first term and go off of that. So we can do the second term and work off that. Cool. Number 22 is probably the same kind of problem. So number 22, let me write it out. I don't know the answer right now. -3, -1. Oh, I know it. All right. Given that they go from negative to positive like that, it's probably more of a sum kind of thing, and that looks like it's what it is. We add 2, and then 3, and then 4, and then 5. And then it kind of, continues on the path. So, ... So, we can do the same thing here. The first term is -3, and then the next term takes the previous term, and it's adding the term's position. So, the second term needs to add 2 to it. The third term needs to add 3 to it, etc. from the previous term, starting from -3. That's where I'm going with those. Okay, in exercises 23 to 26, write a recursive rule for the sequence shown in the graph. So we have to write out what that sequence actually is and go from there. Now, they are getting a little bit more particular in, pardon me, I need to, let me clear my throat for a second. Okay, what I was going to say was, they're doing a lot of f of zeros lately, so I don't know if they're considering that to be their first term or not. Given that n, in my book, n needs to start with 1. For sequences, n needs to start with 1. That doesn't mean you can't have an f of 0, but I'm really all about the first term for that. So I'm going to keep the graph where it is. I'm going to say that that first term is 1. Oh, actually, before I even do that, but the first term is 1, right? So I'm going to start with 1. It's 1, then 2, then 3, then 4, and then it keeps moving on, right? So your first term is 1. And listen, that's a part of our recursive rule. We literally have to write that. The next term is adding 1 from the previous term. So it takes the previous term plus 1. And I'm using function notation because this says f of n on it. I should have mentioned that. So I seamlessly went to that without even thinking about it. So I realize I have to explain that to you now. Number 24, same thing this time. Yeah, I don't see an f of 0. So we're going from 8 to 4 to 2 to 1. We're dividing them by 2, which means multiplying by 1/2. So the first term is 8, and then you're taking half of your previous amount. So literally times 1/2. F of n is 1/2 times the previous term. This has been a nice quick stretch. I mean, when we hit word problems, it'll be a different story. And I was going to say error analysis might even slow me down. Number 25. -1. Wait, the scales are by 2s. -2, 1, 4, 7. Looks like a common difference of 3. Arithmetic. First term is -2. Next term is 3 more than the previous term. And then number 26 also looks arithmetic. They scale by 2s as well. So 4, 2, 0, and -2. So we have our first term, and we have our common difference of -2. So subtracting 2 from the previous term. Again, a lot of these still feel very IM1-esque. I'm not complaining. I'm questioning. Where do they get their decision-making ability by throwing this in the mix? Okay, in exercises 27 and 28, describe and correct the error in writing a recursive rule for the sequence 5, 2, 3, -1, and 4. Now, in my head, I'm seeing 5 minus 2 is 3, 2 minus 3 is -1, and 3 minus -1 is 4. So it's a subtraction of 1 with the other. What they wrote is good when it comes to the rule. The problem, and they're actually correct, even the order that they have it. This is 2 terms before minus 1 term before. It gets boom. That's actually correct. What's missing is indicating what the first 2 terms are, right? If I say, hey guys, I want you to, for this rule, I want you to subtract the first term minus the second term, and then, keep subtracting like that. They're like, great. Can you give me some numbers? Like, oh, yeah, of course. The first two terms are not mentioned. Whoops. A little too small. The first two terms are not mentioned. So, as far as in overall, like, that's all that's missing. Everything else is actually right. So, a sub 1 is 5. A sub 2 is 2. And your entire rule is what they have. Take that 5 and subtract it with the 2 to get the third term, etc. So that'll be the correction. Number 28, beginning with the second term in the sequence, each term a sub n is a sub n minus 1 is minus 3 is a recursive rule. Well, this is very wrong on number 28. 27 was very close. It actually had that idea of recursion with the previous two terms. We're only subtracting 3 the first time. After that, we're not at all. This is not an arithmetic sequence. Now, I already wrote the rule up top, so I don't really know how to correct anything beyond what I already wrote. But they wrote it as an arithmetic sequence. Which ours is not. This only worked for the first two terms. And nothing else afterward. Now the correction is see this above. We're doing the same rule as that one, so I can use that. Okay, in exercises 29 to 38, write a recursive rule for the sequence. So this time they're giving us an explicit rule, and we have to come up with its recursive rule. So for number 29, we have a sub n equals 3 plus 4n. By its nature and appearance, this is an arithmetic sequence. In this arithmetic sequence, we need two things. The first term and the common difference. Now the common difference here is 4. That's derived from the number that multiplies by n. Every time n increases by 1, that's another 4 that's added. That's how that works. It's like the y equals mx plus b. It's like your slope. A sub 1, you substitute 1 into here, and it's as simple as doing the 3 plus 4, which gives you 7. So your rule as a whole, literally a part of it is the a sub 1 part, right? A sub 1 is 7, and a sub n takes the previous term plus 4, common difference. Boom, we got it. These will go relatively quickly as a whole. I don't really have much to say beyond what it is we're doing. Even after this problem, I will really quickly speed up even with the a sub 1 because that's a part of the rule answer. So with this one, we have, once again, we have a common difference of -8, the thing that's multiplied by n, and a sub 1 is -2 minus 8 times 1. Remember, you can always find your first term by substituting 1 into here, but this one doesn't spell out the first. -2 is not your first term. It's kind of your 0th term because of the way that this is written. Yeah, so, but here's the thing. We're just subtracting 8. 8 times 1 is 8. So that's -10. First term, -10, and any successive term, you take the previous term, minus 8. Number 31 and 32 are also arithmetic, so I think these can go as fast as what we've seen, so I'll call them out loud as they are. A sub n equals 12 minus 10n. We have a common difference of -10, and 12 minus 10 gives me 2, which is our first term. So your first term is 2, and your next term, we got to subtract 10 from any previous term. Again, apologies if those feel kind of fast. They just take on the same nature as all the previous problems before, and I don't really know what else to add to it, like in terms of commentary. Feel free to add what you need to make sense of the problem, of course. This is just a guide for efficiency's sake at this point. But you do need to write out what the first term is, and the first term is 9 minus 5, which is 4. This is a common difference of -5. So a sub n is a sub n minus 1 minus 5. Now, all of those were arithmetic sequences. Upcoming, given the exponents, are geometric sequences, and these geometric sequences are taking on its specific explicit rule, which even goes all the way down to the first term being that number that's in front, that 12 for number 33, and the -7 for number 34. Because it's the n minus 1 power, so if I substitute 1 into there, I'm just going to get 12 out and -7 out, respectively. So on number 33, we have, once again, a geometric sequence, which means we need first term and common ratio. They are showing you them on the problem right there. The first term is 12. The common ratio is 11. So in the rule, I'm just going to rewrite first term as 12 all over again, but the next term takes 11 times the previous term. I'm going to erase that little dot that I put. That was an accident. 11 times the previous term, which the numbers get big. It's a good thing I don't have to write any of the, like the first 6 terms. Number 34, same thing. Different answer, but same. It's geometric. We have a first term of -7, a common ratio of 6. So first term is -7, and any next term is 6 times the previous term. I'm going to enhance that -7. Zoom enhance. Boom. All right. Anything changing here? Not really. No. They ran out of things to do. We're back to an arithmetic sequence again. Just because we have decimals makes no change in the kind of thing we're doing. Hey, what's 25 minus, or 2.5 minus 0.6? 1.9? I agree. So the first term is 2.5 minus 0.6, which is 1.9. The next term is the previous term minus 0.6. That is our common difference. I do, at the same time as anything else, and I mentioned this before, I do feel bad on these problems. Granted, I am halfway through the video now. Not through the video, but through the problem set. I feel bad on these problems if I don't give extra teaching things to mention, but I'm giving you the level of efficiency that I want you to recognize for these things. You need the first term in common difference. The first term is substituting in 1, which is -1.4 plus 0.5. I have nothing more to say than that, because that's what it is. And this is taking the previous term and adding the common difference. You want to recognize where the common difference stems from once you understand how explicit rules are written, specifically for arithmetic sequence. And now geometric sequence, again, no change in what there was before. It's an exponential. It is an n-1. Therefore, that first term is the number you see in front, and the common ratio is always the number you see that's the base of your exponential portion of this equation. So the first term is -1/2, and 1/4 is your common ratio. Pretty nice. Number 38, last one from this set. And then I do believe the next, I don't know if it's the very next set, but we are going to have to go from explicit to recursive. So we might have another drill and kill coming up like these, where it's kind of like, I don't have much to say. Although we are going to have to simplify our explicit rules in those problems. So your first term this time is 1/4. Your common ratio is 5. So we're going to quintuple. Well, oh no. We're going to quintuple our previous values. So 5 times a sub n-1 there. Okay. Let's see what's coming next. Oh, here's where we're going to do those, but we start with these two. Number 39, rewriting a formula. You have saved $82 to buy a bicycle. You save an additional $30 each month. The explicit rule a sub n equals 30n plus 82 gives the amount saved after n months. Write a recursive, well, I guess we haven't lost this yet. Write a recursive rule for the amount you have saved n months from now. It's the same answer here, right? You need the first term. 30 times 1 plus 82 is 112. And then your rule is the next month, you take the previous month's amount and save another $30 on top of it. Given the first month of amount saved is $112. After a month, that is. Number 40. Rewriting a formula. Your salary is given by the explicit rule 35,000 times 1.04 to the n-1 power, where n is the number of years you've worked. Write a recursive rule for your salary. So it is just more of the same. I don't really this is still this is geometric, and you have first term and common ratio given the n-1 nature. So your first term is $35,000 for that year. It looks like we're increasing 4% per year. Not that they want us to interpret it. But you are multiplying your previous year's salary by 1.04 to get dat raise? Is that what they said? No, it's just the salary. That's how salaries kind of work that way. Okay, in 41 to 48, write an explicit rule for the sequence. Don't mind if I do. So this time we're given the recursive rule. We just have to spell out what kind of sequence it is, arithmetic or geometric. determine its common difference or ratio based off that, and then write it given the formula thing that we know for it. This is arithmetic given a common difference. We're subtracting 6 each time. Our first term is 3. The explicit rule that we generally write, we start with our first term 3. We add our common difference, n minus 1 times, like that. That could be n answer, but they tend to go more for the distribution portion. 3 minus 6n plus 6, which is negative 6n plus 9. They've been doing a little bit more of writing like 9 minus 6n. I'm more in the mx plus b kind of form with it. So that's how I'm going to write that one. Number 42, also an arithmetic sequence because it says you're adding 7 each time from the previous value starting from 16. So we're going to show exactly that regarding our explicit rules, a sub n minus 1 plus 7. And I want to get into that notion of being quicker over time. So let's actually do it for this one. A sub n equals, I'll do 16 plus 7 times n minus 1. If I distribute 7, it's 7n minus 7. And 16 minus 7 is 9. So this becomes 7n plus 9. Again, there's speed I want to add to it. Other versions of speed that we've mentioned, because we've done this before, is you find the 0th term by subtracting 7, right? If 16 is the first term with 16, 23, and 30, yada, yada. The 0th term is 9 by subtracting 7 from it, and that 9 spits out right there, right? That's what we're getting from it. So you can even go 0th term form without having to do the distribution and then do that. So I imagine I might do that at some point if the numbers are good. That's for arithmetic, though. Geometric, like this one's geometric. Geometric sequences, we don't have to simplify more. What we see is what we get, given that we can keep that n minus 1 as it is. A sub n equals 3 times a sub n minus 1. First term is negative 2. Common ratio is 3. So your explicit rule is negative 2 times, times 3 to the n minus 1 power. That's it, and that is all. No simplification necessary. Give me more geometric sequences, please. Number 44. They gave me another geometric sequence. Okay. A sub 1 is 13. A sub n is 4 times a sub n minus 1. So 4 is your common ratio. So a sub n takes the first term times the common ratio to the n minus 1 power. Number 45. A sub 1 is negative 12. A sub n is a sub n minus 1 plus 9.1. That makes 9.1 our common difference in negative 12, the first term again. We can go back to our thing. It's negative 12 plus 9.1 times n minus 1. In a future problem, if the math ain't too hard for us, I'd like to just subtract 9.1 from here and say what it is. Negative 21.1. But let's go ahead and play the distribution game for this one. Negative 12 plus 9.1 n minus 9.1. Now you have to do negative 12 minus 9.1. So you can see why I'm saying what it is that I could have done to alleviate any extra writing. At some point, I'd like to do that. Alleviation. Is that a word? Because I did it in section 7.2. I think that, or 7.1, whichever one that we were writing a lot of arithmetic sequences on. I did do it at the time with it. Number 46. We have a first term of negative 4 and a common ratio of 0.65. No amount of decimals will really phase what it is that we're writing, especially for the geometric ones, because we don't actually have to calculate anything. It's literally just a writing like that. Do I really need to do 70 problems of these? I'm asking the book. I'm saying, like, hey, book writers, do you really need to give this many? At some point, you know what? You need to give kids some drill and kill for this stuff. The way you get better at something is through practice. I mean, so if you're assigned these problems, if you want to try all these problems out, get that practice in. Do it till you feel you got it. I mean, that's true for anything in life, right? Sports and music and stuff like that. I mean, anything that you do. Problem is my videos don't seem to improve. I've recorded like 500 videos. My videos sometimes I think about that sometimes, going like, have I gotten better in video making since, I don't know, in the past 8 years or so. Not really. And heck, I did a full year plus or whatever of distance learning teaching and tutoring on Zoom and stuff like that through COVID. Oh gosh, none of that. Anyway, we got a common difference of negative 1/3. This one might look a little bit trickier. I got this guy here, first term. We're subtracting our common difference n minus 1 times an incomes distribution of the negative 1/3. So this is 5 minus 1/3 n plus 1/3. And we got to do 5 plus 1/3. And I know you want to say 5 1/3, but 5 is also 15 thirds. Is that right? 15 thirds? 15 thirds plus 1/3 is 16 thirds. So that's how I want to write this one. Negative 1/3 n plus 16 thirds. That's my go-to. Number 48, last one of this set. A sub 1 equals negative 5, and a sub n equals 1/4 of a sub n minus 1. Now, if there's one thing I need to state on this, although I've been doing it for all the problems, and I will continue to do it, and I've stated it in the past, I've been using parentheses for the geometric sequence rules the whole time, and it hasn't been so much a requirement for integers, but it is for fractions and negative numbers. So this 1/4 is required to be in parentheses here, whereas for whole numbers it wouldn't be. Negative numbers it would as well when it comes to raising the powers. And I've stressed that, I think, enough that I hope it makes sense. All right, we get to rewrite a formula a couple times, so I think it's just going to be a lot more of those two, but they give you some context, so we can explore what other kinds of problems they might ever say with them. A grocery store arranges cans in a pyramid-shaped display with 20 cans in the bottom row and 2 fewer cans in each subsequent row going up. The number of cans in each row is represented by this recursive rule. So it's interesting that, I kind of wish that they made us come up with the recursive rule given the information. That would, maybe they're getting us prepped for when we have to do it in a bit. But here's the recursive rule. First row is 20, bottom row is 20 cans and 2 less from each one. Write an explicit rule for the number of cans in row n. Okay, so 20 cans and minus 2 times n minus 1. We distribute the negative 2 there, and that's negative 2n plus 2. 20 plus 2 is 22, so we get negative 2n plus 22. Cans. Number 50. The value of a car is given by the recursive rule. A sub 1 is 25,600, and a sub n is 0.86 times n minus 1, where n is the number of years since the car was new. Write an explicit rule. So if I'm to give you some context for this problem, the car begins at $25,600, and then every year it's becoming 86% of what it was before, which means it's losing 14% of its value. Now, none of that is relevant to what we have to do for this problem. Maybe a future problem would, but not this one. This is a geometric sequence. That's our first term. This is our common ratio to the n minus 1 power for that first term. That is our answer. Number 51 on using structure. What is the 1,000th term of the sequence whose first term is a sub 1 equals 4 and whose nth term is a sub n minus 1 plus 6? Justify your answer. Now, we haven't spoken on, and who knows, maybe it's going to be part of the questions. What are the pros and cons of each kind of rule base? A lot of people don't like the idea of recursive rules. When you look at the formula, you're like, this just looks hideous. But you have to remember, this is how we tend to think. If you see a pattern, hold on, I have to write this correctly. If you see a pattern that says, 4, 10, 16, 22, etc., you're just going to say plus 6, plus 6. Everyone does it. So we think recursively. So there's a benefit to that. Plus getting the next terms right after that. Just keep adding 6 each time. That's good. But the 1,000th term, I don't want to keep adding 6 over and over and count up till I get it. There are some students who will literally do that if they don't have any other means of getting it right. And at all costs, they have to get it right. But we also have explicit rules for that. And explicit rules are specific for that reason. Meaning they're specifically made. Like, that's why the formula is what it is. Why is it 4 plus 6 times n minus 1 for this arithmetic sequence? Because from 4, we're going to add 6 one less time than the term we're looking for, because 4 is the first term. How many terms is 1,000 away from 1? It's 999 away. That's why this rule works. 1,000 minus 1 is 999. We're going to add 6 999 times from 4. That's how it works. I could plug in 1,000 right here and get the 999. I'd rather actually honestly distribute this one, as they probably would as well. because it's easier to do 6 times 1,000 than 6 times 999. There are ways around that, of course, but we're just going to write it like that. So what is a sub 1,000? 6 times 1,000 minus 2 is 6,000 minus 2, which is 5,998. Was there context to this question? No. 5,998, the answer is B. Oh, and I used explicit rules because you can plug the number into the equation, boom, like that. See, in a recursive rule, I can plug in 1,000, but that says take the 999th term plus 6. I don't know the 999th term. I need to know the 998th term, and so on all the way till down the first term. So explicit rules are really good for that kind of thing. All right, number 52. What is the 873rd term of the sequence whose first term is 0.01 and whose nth term is 1.01 times a sub n minus 1? Justify your answer. So this one's interesting because I'd assume there's rounding involved, but because it's multiple choice, we can figure out which one to choose with that. So here's our recursive rule, first term and all. We're going to multiply 1.01 each time there. So let's write an explicit rule based off that. Take the first term and multiply by 1.01 this many times. So if I want to find the 873rd term, I do 0.01 times 1.01 to the 872nd power. That minus 1. Let's go to the calculator and see what it spits out so we can understand what kind of answer we should be writing. 0.01, because I don't know. But this is kind of nice because we're multiplying, 1.01. It's a number just more than 1. So your number just increases a little bit each time, which means it might not increase that much as an overall, even with 872 changes. Yeah, 58 point whatever. That looks like this is going to be the A answer. So I'm going to write a lot of what that number says. 58.6459381, which is about 58.65. That's going to be A as an answer. So it's increasing very slowly over time. You get a 1% increase. It's basically saying this. You start with a penny, right? $0.01. You start with a penny, and each day your bank increases your, how about each day? Your bank increases your penny amount by 1% each time. How much money will you have in the bank after 873 days? Or on day 873, you'd have $58.65. All right. It's like the amount I get on my YouTube channel, kind of like that, right? I don't get much monetization at all. I remember telling another teacher about yeah, I've accumulated, less than $100 over the course of my channel. Now it's grown a little bit. I don't really look at it though. But they're like, hey, it's a few cups of coffee. I'm like, I don't drink coffee. Number 53, problem solving. Looks like we might hit some actual word problem basis now. So this might slow to a crawl a little bit. Just got to be ready for that. There was a lot of drill and kill. Probably not so much anymore. An online music service initially has 50,000 members. Each year, the company loses 20% of its current members and gains 5,000 new members. Okay, I don't know if I'm going to do anything with the drawing. I don't think the drawing's going to help me much. Write a recursive rule for the number a sub n of members at the start of the nth year. So the way that this thing would kind of work is this. We got 50,000 to begin with. And each year we lose 20%. So that common ratio is 1 minus 0.2, which is 0.8. Losing 20% is taking 80% of what you have. So we're going to take 80% of what we had in the previous year. But you also gain 5,000 new members. So it's that algorithmic version of what you're doing as a total. That's the recursive rule, that's part A. That algorithmic total is happening. You lose 20%, but also gain 5,000 of them. And it kind of changes. I could confirm that next number would be 45,000 because 20% loss of 50,000 is 10,000 members lost. So that's 40,000. But then you add 5,000 to get 45,000. So that tracks. Part B. Find the number of members at the start of the 5th year. So even the book was using, the calculator at this portion. So I'm going to do the same thing. Here's what I'm going to do. I'm going to start with just the number 50,000. Literally, I'm going to press 50,000 and just enter. That way, anytime I recall this answer like that, it's just that number. Okay. Now I'm going to take my formula, 0.8 times my previous answer, and then plus 5,000. This will show me after for year 2. Wait, it initially has this many in each year. So they say at the start of the 5th year, I believe we need to find, this is like the year 1. No, this says beginning of 2nd year. So it literally says beginning of 1st year here, beginning of 2nd year. So that's the 2nd year, okay? The 3rd year, I just have to press enter now because it's going to take the previous answer, which is this one. It's going to do 0.8 times that number plus 500. So here's the 3rd year, 4th year, 5th year, at the beginning of the 5th year. So 35, and I'm going to literally like just copy paste that into here so you have an idea. Like that's my work. I'm not going to do the work as a full set, right? At least that's not my intent. That's recursion. That's recursion at play. And so the answer is a sub 5 equals 35,240 members. So that's at the start of the 5th year. Part C, describe what happens to the number of members over time. Now, this is the really cool part with the calculator. The lecture portion kind of showed this as well. Just keep pressing enter and show that conversion. Watch what happens over time as the thing weeds out. Because what we're really doing now, see that convergence? We are taking 20%, we're losing 20% of our members, and then we're adding 5,000. Well, what does it mean to take 20%, to lose 20% of 25,000? That's to take 5,000 away. And then to add 5,000 back. You get back to 25,000. It converges to this number over time. So I don't know how they want to say it best. Just eventually, that's the convergence value. The number stabilizes at about 25,000 people. It converges to 25,000 people. The number stabilizes at about 25,000 people. Members. I think they used that word stabilizes on that last one. Oh, you don't see what I'm typing. I apologize. Okay. I'll keep it on the screen there for a second longer while I move to this next one. This looks like the same kind of question with what we do, just describe what happens over time. So get ready for something very similar. Number 54. You add chlorine to a swimming pool. No, you add chlorine to a swimming pool. You add 34 ounces of chlorine the first week and 16 ounces every week thereafter. Each week, 40% of the chlorine in the pool evaporates. I don't know. That was confusing. I'm trying to see what I'm looking at. Okay. In the first week, you have 34 ounces. 16. You add 16 every week thereafter. So each week, I'm adding 16. Now it says 40% evaporates. I'm trying to think as to whether they mean, well, if 40% evaporates, that means you have 60% left. But what I need to consider, and I think I got the answer in my head here, but if 40% evaporates, you get 0.6. That'll be the common ratio portion, and we're adding 16. I just need to know if we are taking 60% of what we added, or if it takes 60% and then we add that amount. I think we add the amount after. That's the idea of the evaporation. They should have said that first, though. So they should have said, I added 34, and then after 40% evaporates, I'll be adding 16 ounces. Because that's the idea, I think, is it evaporates, and therefore you add more. That's how I'm seeing it, anyway. I don't know if that's right. That's what I'm going with. So that's my part A. Because that's what they wanted, right? A recursive rule. Part B. Find the amount of chlorine in the pool at the start of the third week. So that would be, this is the first week. So let's do the same thing we did last time. We had 34 to begin with. Oh, it's 25,000. We had 34 to begin with. We're going to take our previous answer times 0.6 and then add 16 to it. This is the second week. This is the third week. What was this answer in? 37.84. ounces of chlorine. So 37, oh, A sub 3. A sub 3 is 37.84 ounces of chlorine. Cl is the elemental symbol. My computer fan's buzzing. Hold on. See if I can. Oh, now it got louder. Hold on. Let me try and find a way to fix this. Give me 1 second. Okay, and the giant score is still 0-0. Part C, describe what happens to the amount of chlorine in the pool over time. Now, even just from these two ones alone, I mean, it's increasing. But it's increasing by less over time already. It was plus 2.4 here. Now it's plus 1 point something. So if we just keep increasing it, it's going to increase over time, but by less over time. It's getting closer to 40 ounces, and I assume that's where it'll converge. 40. So it's that same thing, right? 60% of 40 is 24. And 24 plus 16 is 40. So that's that restorative balance. Once you hit that number, eventually it stabilizes. So that's the same thing as this one. So the amount of chlorine in the pool stabilizes at around 40 ounces. The amount of chlorine in the pool over time. Okay. Number 55, open-ended. My choice. Give an example of a real... Oh, I'll have to make one. Of a real-life situation which you can represent with a recursive rule that does not approach a limit. Write a recursive rule that represents the situation. So approaching a limit would mean if you had a common ratio that was less than 1. So like the last question, like the last two questions, they had a number that would kind of have that shrinkage thing over time, and you don't want that. We want something that just increases over time. I could do... I'm thinking baseball right now. Just baseball's on. You have a baseball card collection. You have a baseball card collection of 1,000 cards. Every year, you purchase 5% more. Where's the percent? 5% more cards than the previous year. Now, why is this not a recursive rule? You're thinking 5%, Mr. Robinson, isn't 5% 0.05? Yes, it is. Our common ratio isn't 0.05, it's an increase of it. It's 1.05. So your rule is my rule is a sub 1 is 1,000 and a sub n is 1.05 times a sub n minus 1. That doesn't have a limit. That'll keep increasing. So if I go to the calculator for that one, it says describe what happens over time. Whoops. If I said describe what happens over time of this, times previous answer like that, that ain't slowing up. That's speeding up, right? Pretty soon I'll have 10,000 cards, like nothing. And then just, wait, can I press enter? There we go. And then like nothing. When am I gonna have 1,000,000 cards, right? But that's the idea. It's not converging. It's speeding up over time. I'm gonna hit million as fast as I'm done. Anyway, so that's the idea, right? As long as the number's more than 1, well, even if it's 1, I think it'll work out. Number 56, give an example of a sequence in which each term after the third term is a function of the 3 terms preceding it. Write a recursive rule for the sequence and find its first 8 terms. Give an example of a sequence in which each term after the third term is a function of the 3. Oh, so we can just make up a thing with it, right? So let's just start to write things out. If my first 3 terms are 1, 2, and 3, because these can be random. These can be whatever. And then the terms after that are based off these ones. Should we just add them? 1 plus 2 plus 3 is 6. 2 plus 3 plus 6 is 11. I don't know why I'm slowing. 3 plus 6 plus 11 is 20. 6 plus 11 plus 20 is 37. 1, 2, 3, 4. And then 11 plus 20 plus 37 is 68. I think that's right. So First term is 1. Second term is 2. Third term is 3. The next terms, you got to add up all dem terms before. Like that, right? It's just the sum of those ones literally straight up from there. Okay. Number 57. Modeling with mathematics. You borrow $2,000 at 9% annual interest compounded monthly for 2 years. The monthly payment is $91.37. Find the balance after the fifth payment. Find the amount of the last payment. Okay, now there was an example on this. They even say see example 7. So we can kind of model after it a little bit, especially given that they use a spreadsheet. So I might have to do a spreadsheet version of this afterward, especially if I want to kind of track the numbers the right way and see which one's what. But we're going to come up with the rule to begin with. So you borrow $2,000 at 9% annual interest compounded monthly. So your first thing is $2,000. I believe that's how it would work, kind of something like that, right? And then from there, the 9% annual interest compounded monthly, your common ratio has to divide the 9% by 12. Now, 9/12 is 3/4, so 0.912 is 3/400. There's a better decimal than that. What? 0.0, wait, hold on. If 9/12 is 3/4, which is 0.75, then this is 0.0075. There we go. That's easier to write. So we have that. So your rule, we're taking 0.0075, or are we? It's interest. So we are 1 plus that, right? 1 plus 0.0075 times a sub n minus 1 times the previous month. But our payment we're making is that's the wrong number. 91.37. 91.37. So this is the rule that we're coming up with on a monthly basis. It says find the balance after the fifth payment. Now, your first payment there, once again, is $2,000. Boom. So here's a rule. I'm going to do a spreadsheet thing. Give me 1 second. I'll pull this up on Google Sheets. Okay, so I pulled up a spreadsheet. Now let me find it. Okay, I pulled up a spreadsheet. And what we'll do is the first one's $2,000. Is that the payment? The only thing is I got to figure out is if this is the payment. I know 2,000 is a part of it, so I'll figure out whether 1 needs to be here or 1 down below. But for a moment, I'm going to place 2,000 there and figure out which way I want to arrange that. I might have to do this slightly different and shift this one down. But these numbers, I can just do the previous number plus 1. So these numbers will kind of go down. We did it for the first, we're going to do it for the first 2 years. We're going to go to 24 like that. These numbers take equals. This number times, no, not plus 1. What? This number, no. What's the plus? No, don't autocorrect. Don't tell me what I want. 1.007. That's my inner voice to this thing. 0075. I hope I have the decimal thing on that right. Times the previous value. I don't know if I need these numbers. Minus 91.37. Now I can fill that down this way as well. I might need to do it at least one more time, it looks like. So I think that 2,000 doesn't quite qualify, which is why I want these numbers written so I can recognize what represents what. The 24th month would be this one. And that probably is right because it goes negative. We'll talk about what that negative means later. But give me a second. I need to see the question again. Find the balance after the fifth payment. So given the fifth payment, I think this number is going to represent the fifth payment there because that's not a payment. So after payments, boom, first payment, second, third, fourth, fifth. So they also did this round feature. Let me see if I have this right. They're going to round this number to 2 decimal places like that if they want money. So we can do it like that. Boom. Now, why did that turn positive? This was negative. Why did that turn to positive? That's negative, right? That's a negative sign? So, that should stay negative. Okay, hold on. I'm sorry. Give me 1 more second. There was another feature. Let's just truncate. I don't have to use the round feature. Let's just do There we go. Let's do it like that. Now it's negative. That was weird. Okay, so we have these numbers here. So my fifth payment will be $1,612.38. So let me write that. So part A sub 5 is $1,612, and did I say 38 cents? I'll check that. Part B says find the amount of the last payment. So the idea here, let's go back to the sheet. So the last payment is for the 24th month. And I'm sorry, you know what? Last time I did a spreadsheet, I recognized in my video I wasn't very zoomed in. Let me zoom in for you. Is that better? Sorry about that. So the last payment, when rounded, is with another cent that needs to be used with this. So, well, you know what? It says 0.135. I wonder if I should round it to 2 cents added or not. I'm just going to do the 1. I'm doing a rounding thing. Anyway, we owe an additional cent on top of what we have, right? Our payments... let's see, how do I say it? Our payments utilize that formula, right? This 0.75% of what we have and take away, and we pay $91.37. But if we owe, because we're doing this until our payment is fully paid off, so if the balance there is negative 1 cent, and we have to make the payment of $91.37, then we have to combine those together. So the last payment is going to be that 91.37 minus, is that how we'd say it though? I guess the minus is what we're always subtracting. So let's take that number minus 91.37, and that's negative 91.38. That means the amount of the last amount paid is 91.38. 91.38 paid on last month, the 24th month. Okay. I'll go a lot faster on this next one now that I have the sheet open, now that we've explained it. We'll go off that. Number 58, because I think 58's like that. Number 58, you borrow $10,000 to build an extra bedroom onto your house. The loan is secured for 7 years, that's 84 months, at an annual interest rate of 11.5%. The monthly payment is $173.86. The last one was compounded monthly. This one's not compounded monthly. So this one, I might work this one differently. Because I might think, I might do this in terms of years this time. So that monthly payment, I might just multiply the monthly payment by 12. I want to see if this kind of works out. So that's 7 years. It does say monthly payment. Says annual interest rate, but it doesn't say compounded monthly, and there's a difference between the two. I got to think about what to do with that one. I'm one of two minds. And I don't know of which mind I should go. I'm going to try this one of two different ways. I'm going to try what I said first. It doesn't see, this one says compounded monthly, which means that's where we do the divided by 12 thing. We get to do that each time. This one does not say that. Am I missing it? You borrow here, the loan secured for 7 years and annual interest rate. This monthly payment is that. It doesn't say compounded monthly. So, I'm sorry, I keep saying that out loud. The first term is 10,000. This is 1 plus the 11.5% like that, if annually. And 173.86 times 12. How much I pay in the year. They're monthly payments. Let me pause and think about which way I want to do this. Hold on a second. Okay, I feel like I just want to go off the premise that the examples have. They don't say compounded monthly, but I'm going to use compounded monthly. So, because otherwise there's too much involved with the fourth payment and the last payment where we'd have to do this divided by 12 thing. I don't think it would work out. I think they need the words compounded monthly and it's just not there. So what I'm going to do is compound it monthly. I got to calculate it though. Give me a second. I should really just use Google Sheets for all this. So 1 plus 0.115. You know what? Honestly, if this number isn't that clean, I don't know if it is or not. Yeah, it's not a clean number. It looks like this. If the number's not clean like this, I'll just use that itself, and I can use that in Google Sheets. So this guy will be the way that I kind of write it. So our rule of a sub 1 is 10,000. We are going to do this compounded monthly bit here for the 11.5% interest loan. Again, I'm no good with finances. So I don't know when it comes to telling like my attorney about it needs to be compounded monthly or whatever. Anyway, so we're taking out a monthly payment of $173.86. All right, part A, find the balance after the fourth payment. Part B, find the amount of the last payment. So part A, it's gonna be the same thing. Let's go to that Google Sheets thing we had before, and I can't find my window. I just have the thing open. And we're going to do 10,000 here. And then this will be, okay, this is where we'll have 1 plus 0.115 over 12. And then we're subtracting, and times the 10,000, subtracting 173.86. Like that. And then these need to apply the same formula. And we need to do it for 7 years. So I need to do this. Give me 1 sec. Let's copy and paste that for now. Let's do this all the way down to month 84. Oh. Hold on. Copy, paste. The only thing that concerns me is whether I'm doing any early rounding before that. I know I have all these numbers like that, but is that affecting, is it rounding other numbers early? That's what I want to know. I just want the exact answers, honestly. Let's see what this looks like. No, it's just those numbers. But that's not negative yet. So, interesting. I figured we would have gotten to negative land with that in mind because that's kind of what they were doing on the last problems. Anyway, month 4, fourth payment is $9,683.38. Or the balance, not the payment. So, A sub 4 is 9,683.38. Part B, find the amount of the last payment. It's secured for 7 years at this annual interest rate. This is where I'm going to be a little confuzzled. Maybe I don't know if my Excel thing is doing some calculating parts a little imprecise, but I figured we would have hit a negative value there. Instead it says 59 cents because that means that I'm still paying 173.86. I think that's how it works. Because I think that we've been doing the difference between these two. I don't know. I might mess up this answer. What's the 85th month? What's that going to give you? 173.26. Yeah, unfortunately, I don't really know too much about these numbers and how they work. I don't know if I'm going to get this answer right on this one because I would have expected a negative number and doing that difference there. I don't know. 7 times 12 is 84, right? Dude, I don't know. I'm not sure. I would have expected a negative answer. So, and I don't think the negative answer is that big because that's the 85th month after that. For 7 years. You borrow 10,000. Sorry, I'm looking back at the problem. You borrow 10,000 to build an extra bedroom. Secure for 7 years. Yeah, I don't know. My calculation's not really giving it to me the way that I want it to. So, actually, I don't know. I'll stew on it for one more second, and if I don't know, I don't know. I apologize. Okay, I have some interesting new developments, and it makes me want to go back to the last problem. There's not much change of an answer, but I did perceive the last problem wrong. So one of the things I'm doing differently is not really dealing with the negative part anymore. It's just about the last month. I think that I was confused with the textbook, and it said normally the last one is negative or something like that. I don't know what they said, but I read the thing wrong in that the negative means an overdraft, which means money they owe you back. But the last payment is what you add with your monthly payment bits as an overall. The other thing is Excel has a difference in its rounding formula versus the truncating of the decimal. So what I just did, I'm in Google Sheets right now. What I just did was I changed my code to round to 2 decimal places, because that's what I saw last time. And this is why I was thinking like, whoa, on the last one. This changes this thing to 0.64 as the 84th month. Now, it's still not negative, but that's different from the last number. I forget what the last number was, 0.53 or something, I forget. But it's a different number. The book was using the round thing, so I want to use the round thing, I guess, to be particular with what the book might say. Now, given this overdraft thing, we're going to have our last payment plus whatever this number is. If the number's negative, adding that number subtracts, but this is positive, so we add it. So my belief for this one, and I have to go back to the last problem now, is that we're going to take 173.86 plus 0.64, given how Excel is using that. Now that is 174.50 for the last month paid, because they're still at 64 cents owed. Now what I have to do, I'm going to press the undo button a bunch on my Google Sheets. Give me a second. I just got to keep undoing till we get to that thing we had previously, 1,000, 2,000. Okay, so what we had before, now I'm back to Google Sheets here. What we had before was this information, but what I got to do is change this back to the round feature. I'm going to bring all my decimals back. Wait. Yeah, I'm going to bring all the decimals back the way that they were. And let's use the round feature to 2 decimal places. Because before we got the number like 0.2, right? So I want to use that again. Oh, I got to truncate this though. But 0.2, yeah, 0.02. So let's use that number for this one. And I have to reconsider the way that I wrote this before. I don't do the minus thing on here in general anyway. I take my 9137. Oh, you can't see this. I'm erasing some stuff over here. I'm taking my 90. This is the previous problem, number 57. I'm taking my 9137. I'm adding 2 cents to it. That doesn't change the answer much, but I was doing it wrong. Even if I had the right answer, I did it wrong. Or at least not. I don't know about the Excel thing, the Google Sheets formula, rounding versus truncating decimals, but that's a difference. There's a difference in answers. There's a difference in what we're getting. I don't know why, but there is. So I wanted to follow how the book did that. As far as if the book had an answer, it would probably be more like that based off what they're doing. So hopefully I'm kind of correcting that with this. Again, I don't know finances. This is me working the solution guide video the best I can. I hope you learned something through this. I guess I am. I'm going to move forward. Number 59. Comparing methods. In 1202, the mathematician Leonardo Fibonacci wrote Le Barabacci, in which he proposed the following rabbit problem. Oh, he has a Fibonacci sequence. He's just a Fibonacci dude. Begin with a pair of newborn rabbits. When a pair of rabbits is 2 months old, the rabbits begin producing a new pair of rabbits each month. Assume none of the rabbits die. And here you have a Fibonacci sequence. The problem produces a sequence called the Fibonacci sequence, which both has a recursive formula and an explicit formula as shown. Oh, I never knew the explicit formula, and I still don't. That is crazy looking. Wow. I do know the recursive formula very well. I didn't know there was an explicit version. Use each formula to determine how many rabbits there will be after 1 year. Justify your answer. I guess I could plug 12 into here. I'm like, I don't know if I really want to. But let's figure it out. All right, so after 1 year is 12 months, right? So we got one. Let's use recursive. 1, 2, 3, 4, 5, 6. 5 plus 8 is month 7. 8 plus 13 is month 8. 13 plus 21 is month 9. 21 plus 34 is month 10. 34 plus 55 is month 11. And 55 plus 89 is month 12. 144 rabbits. For the explicit rule, it's got to be 144 still, but we're going to do f of 12, which is 1 over root 5 times 1 plus root 5 over 2. I had no idea how they came up with this part. 1 over root 5. I was going to say there might be a way to simplify the way that we write this. The only thing you could do at most is factor out the 1 over root 5. Write it as a common denominator, but interesting. I got to figure out how they derived that. Okay, calculator. I wonder if I should just use Excel. All right, 1 over root 5. No, not L5. Root 5 times 1 plus, this is where you got to be careful at your order of operations, divided by 2 raised to the 12th power minus 1 1 over root 5 times Do I get 144? Ah, we got 144. All right, so we still got it. Okay, so that equals 144 rabbits. Assuming none die. That's very cool. That's very cool. I want to think about how it's derived someday, or I'm going to look up how that was derived someday. The explicit rule specifically. Number 60, using tools. A town library initially has 54,000 books in its collection. Each year, 2% of the books are lost or discarded. The library can afford to purchase 1,150 new books each year. So probably a lot of the same stuff as before. So we got to write a recursive rule. So part A sub 1 is 54,000. A sub n, we are losing 2% of the books. So 98% remain, not compounded monthly. So 98% remain there of the previous set, and we are adding 1,150 new books each year. Part B, use the sequence mode and the dot mode of a graphing calculator to graph the sequence. I haven't used them before, so I don't know how it works. I'm going to have to look it up. What happens to the number of books in the library over time? Explain. Okay, this might have been something that we saw. If you recall, there were other sections in lectures, if you saw them, where they had an image. Oh, they might have it on this one. Give me 1 second. Let's go back a little bit here. There was an image I saw of something. I ignored it. This one. Oh, there's no... Set a graphing calculator to sequence and dot modes. Okay, I'm going to have to look this up, I think. But I need to see if another section did this, and if so, I'll learn how to do it. I hadn't learned it before. I remember seeing a bunch of different sections that had things and said, this is how you do it with sequences in a calculator. And I said, I'll do it if I have to. I might have to. So give me a sec. Let me see if I can find out how to do this. Okay, guys. I did a little research. Took a second, but, where do I begin? Okay. First of all, hold on. I'm going to quit out this screen so I can show you. All right. First of all, mode, sequence and dot mode. Sequence mode, instead of being in function, I've done parametric, I've done polar, I've never done sequence, which literally is for sequences. Okay. Dot mode is versus connected mode. It's so that you actually just have the individual integers. But I actually zoomed out. It took me a second anyway because I played with the window and stuff like that. Now I went to equation stuff. So here's what I did. You do the y equals. Your n min is like, this is for your domain. So you want to start at n equals 1 for sequences. We generally want to do that anyway. Here's my equation. Now this is that 0.98. And this is your like a sub n minus 1 and plus 1150. Now this u is found using, it's that little thing right there. It's the second 7. So second 7 gave me u, and the n is like your x. You can see here's x for Cartesian. 2 T for parametric, theta for polar, and N for sequential. I never really even thought about that that's what that meant for those different things. And then -1 and all this stuff, made the equation. Now, I made my N min 54,000 given that that was my first term. I think that that's what that was in reference to when I looked it up. They said, make that your first term. Now, after that, I looked at the graph, but what I had to do was play with my window a little bit. I just chose the first 100 terms to be the first 100, years? I just did 100 years worth of stuff. And I did X in the same window range so we could have all those plotted. And then I chose Y somewhere between 50 and 60,000 because I didn't know if it was going to go up or down. So here's what it looks like. Now, these are supposed to be disconnected, meaning this is supposed to be a bunch of dots. And they are. It's just I'm zoomed out so much to 100 years that it's hard to tell. And they're trying to say, they're asking us what value this converges toward. It says, use the mode to, what happens to the number of books in the library over time. And it looks like it slows up, but I don't know what it converges to. So I'm going to keep zooming out. Not zooming out. Let me actually, since they go up, I'm going to have my Y min stay at 54,000, so it can go up from there. It's not quite going to 60,000, not even close really. Let's try 57,000 as a whole. But let's go to 200 years, and let's just make sure that N is still large enough there. Let's go to 200 for that as well, and see if we can kind of see it fizzling. Whoa. Ooh, I have to go a little higher than that, actually. Oh, because 200, duh. So, let's change Y a little bit then. Let's go to 59,000. Maybe I do have to go back up to 60,000. Oh, no, not really. Okay. Certainly does fizzle, though. Okay, let's see what that's kind of fizzling out at. Let's do... Oh, let's do it at 199 and see what's going on. I don't know, let's get around 57,000. I guess I'll keep zooming out. 300 years. So, yeah, I've never used this before. I don't know. You know what I could do? I could probably go to the table. But they said use the graph and the dot sequence. Now we're seeing a lot flatter stuff there. So let's see what value. It's weird to see that mode, that menu without all those other options. Let's see what we're fizzling out at. 57.4. Maybe it's getting close to 57,500 because it just seems to flatten out more and more over time. And that number is bigger. I'm going to say it's getting around 57,500 books. So the number is stabilizing. The number of books appears to be stabilizing around 57,500 books over time. Now I will copy paste that graph thing with this as well. It's kind of ugly looking because I have all the value stuff on there. But wow, yeah, that's a lot for this problem. If the teacher assigns you that, I don't know. That was my first time using that ever. And I'm not going to use it again unless our book asks me to. Okay. Number 61. We still have 10 problems to do. A tree farm initially has 9,000 trees. Each year, 10,000 of the trees are harvested and 800 seedlings are planted. Okay. 10 are harvested. Does that mean they go up? No, they're harvested. It means they go down. Okay. I was thinking like you plant them. They're harvested and 800 seedlings are planted. So you're adding more after some get harvested. So 10% harvested means 90% still remain. 800 planted means you add an additional 800 within the year. So write the recursive rule. That's your part A. Part B, what happens to the number of trees after an extended period of time? Well, lucky for us, we have the sequence and dot modes on our calculator. Unfortunately for them, I'm not going to use that this time. I'm going to go, whoops, no, I'm not going to, in fact, let me bring my modes back. No, I don't know. I might have to use them again. I'm just going to do this thing again. We have 9,000 and we are taking 0.9 of that. I can go to the Excel spreadsheet as well. I'd do anything above that other thing, especially if I have to explore on the graph. So let's use this over time like that and kind of see what it's fizzling out to as a whole. I have an enter button to use. Maybe it's going toward 8,000. Wouldn't you say? Does it go smaller? Yeah, it's going toward 8,000 there. So over time, we're going to have about 8,000 trees in our tree farm. So over time, we'll have about 8,000 trees. Now, it's one of those things where I like to justify that mathematically. Once we hit 8,000, 90% of 8,000 is 7,200. 7,200 plus 800 is 8,000 again. So it makes sense that that's where it leans out. Okay, number 62. Drawing conclusions. You sprain your ankle and your doctor prescribes 325 milligrams of an anti-inflammatory drug every 8 hours for 10 days. 60% of the drug is removed from the bloodstream every 8 hours. So everything's about an 8 hours thing. This is a for 10 days thing as well. This might be one where we use the spreadsheet again, just because that's like 80 hours total of things we got to do. So 325 milligrams is our initial. 60% is removed. If we do it every 8 hours, then we're adding 325 to it each time, right? I take it. I have 325 in my system. I lose 60% after 8 hours, but after that 8 hours, I'm going to take another 325. So to me, the rule states the 60% that's removed meaning I still have 40% that remains, but I'm about to add another 325 to that. Is that right, a recursive rule? Yeah, that's our part A. Part B, the value that a drug level approaches after an extended period of time is called the maintenance level. What is the maintenance level of this drug given the prescribed dosage? I'll stick to the calculator for now. Let's just use that. So we got the 325 as the initial, and we're doing 0.4 times that previous answer plus an additional 325. So let's kind of explore that, just hitting enter a bunch of times and see what it's going up toward. Oh, look at that. 541.6, so like 541 and 2/3. So over time, we have our, I didn't know that phrase, maintenance level. Maintenance level equals 541 and 2/3 milligrams. Part C, how does doubling the dosage affect the maintenance level of this drug? Justify your answer. Well, now we're going to have A sub 1 as 650. Now, I'm not going to presume to know what the answer is, so I'm just going to do this. A sub n is, well, actually I should. You're just adding a sum. Well, it's not in arithmetic, so I don't know. But this 60% is still lost, and you're adding another 650. So let's do that. Whoops. Okay, let's see how that works. Okay, so 1,083 point. Is that double? 541. Yeah, it's double. So what happens? That doubles. The maintenance level doubles. The maintenance level doubles to 1,083 and 1/3 milligrams. Okay. Number 63. I'm going to read this while I drink this one. Okay, so they're talking about fractal tree. Over here, we're building new branches over time. At stage 1, there's 1 new branch. At stage 2, there are 2 new branches. Stage 3, there are 4. Stage 4, there are 8. They're asking you, first 7 stages. So 5, 6, 7. We have 16, 32, right? I'm not drawing them. 16, 32, 64. It's doubling each time. This is a geometric sequence. So what type of sequence? Geometric. This is all about recursive stuff. So part B is probably going to say write a recursive rule. Part B, write an explicit and recursive rule. So Your a sub 1 is 1 and your r is 2. So this is going to be for the explicit rule. It's going to be a sub n equals 1 times 2 to the n minus 1 power. For the most part here, we can just say 2 to the n minus 1 power and you're good. For the recursive, for the recursive rule, we do mention what a sub 1 is. I mean, it's already written there, but we have to do it again, I suppose. For the recursive rule, a sub 1 is 1, and a sub n is 2 times a sub n minus 1. We got some both. It's kind of an easier question. Number 64. Thought-provoking. Probably a harder question. Is this like a piecewise function? Let a sub... Yeah, sort of. Let a sub 1 equals 34. Then write the terms of the sequence until you discover a pattern. For the next term, we'll take half of it if a sub n is even, and we'll do 3 times a sub n plus 1 if a sub n is odd. This is something I almost want to try and do on this Google spreadsheet thing as well if this takes too long. So a sub n plus 1 equals, so we're going to basically divide it by 2 if it's an even number, if even, and we're going to do 3 times our number plus 1 if odd. So it is even to begin with, right? So 34, half of it is 17. Now it's odd. We're going to triple it plus 1 to get 52. Half of it is 26. Half of it is 13. Triple it plus 1 is 40. Half of it is 20. Half of it is 10. Half of it is 5. Triple it plus 1 is 16. Half of it is 8. Half of it is 4. Half of it is 2. Half of it is 1. Triple it plus 1 is 4. And then 2 and 1, etc. It looks like it's going to repeat that the rest of the way. Do the same thing for a sub 1 is 25. Now 25 is not in this list. So we'll start with 25. Triple it plus 1 is 76. Half of it is 38. Half of it is 19. Triple it plus 1 is 58. I imagine we're eventually going to get back to 421. Half of it is 29. Triple it, 87. Plus 1 is 88. Half. Triple plus 1 is 34. Oh, and then we get to here. ... 421. Etc., etc. So we hit 34 and then we got there. So eventually we get to 421. Now that's something that you can do. I almost want to pause to make sure that I get this right, but I want to type like a formula thing into Google Sheets to show you that same kind of thing. Instead, start with any number and then apply that thing, and then it would always work. But I need to make sure I have the code thing right. But basically, I need to see if the mod for, you know what? I can do it with you here. I just need to see if this mod function works. Give me 1 second. I'll clear out this other thing. I'm always, I'll get rid of this. For mod 3. Does that work? Oh, equals for mod 3. Will that work? No, it doesn't work. Mod. Can I type, is mod a function? Mod for 3. Okay, that does work. Basically, mod is a remainder. So I can say if, let's start with 34. If this number is even, basically, if I do a modulation of this number in 2 and it's 0, then we will divide this number by 2. If not, we will do 3 times this number plus 1. Let's see if this works. 17, copy, paste. Okay, watch this. Copy, paste. Boom. All right, check this out. So now we have this sequence of what we did here. This is kind of cool. So if it's even, we'll divide it by 2. If not, we'll do 3 times a plus 1. You can see 421, 421, 421. So you can do this with any number. We can start with any number we want. What did they do after that? 25. So for 25, whoops, hello. 25, same thing. Eventually hits that 421. What if we do it bigger? Let's do 631, or let's do this number. Boom. And then eventually, oh, I got to keep going. Eventually, oh, not yet. This might take a little bit longer. Oh, I don't know. Oh, I don't think we ever confirmed that eventually every number hits 421. Hold on, let me zoom this out. I'm going to copy paste this for a while. I'm going to go way down to 1,000. Oh, shoot, that didn't work. Sorry about this, guys. I'm almost done. I'm really playful with some of this math stuff whenever it's like this. Copy and paste. Okay, eventually we hit 421, but how long did it take for a number like that? Right here. It took the 150th kind of area right there to hit it. So eventually it goes though, right? With every number, with every integer, I guess it should work. I don't know about negatives. Negative 25. Doesn't look like negatives work. I think it's repeating another sequence there. So with positive integers, I assume it's always going to work. With decimals, that doesn't make any sense. So I think it's positive integers this works for. Anyway, I wanted to toy with that. Okay, let's keep going. Number 65. Modeling with mathematics. You make a $500 down payment on a $3,500 diamond ring. You borrow the remaining balance at 10% annual interest compounded monthly. The monthly payment is $213.59. How long does it take to pay back the loan? What is the amount of the last payment? Justify your answers. I might have to do, again, one of the Excel spreadsheet things again, so I shouldn't have lost. I can undo. $500 down payment on a $3,500 diamond ring. Okay, well, so I'm going to start at 3,000, pretty much. So A sub 1 is 3,500 minus 500, which is 3,000, which is 3,000. You borrow the remaining balance at 10% annual interest, compounded monthly. That means I'll get that 0.1. 0.1 divided by 12 is not going to get me anything great either, so I'm just going to do that this way that I did last time. 10% compounded monthly. Boom. That's going to be my common ratio. I multiply each time. But we are making a monthly payment of $213.59. So when it comes to this sequence, I'm going to do one of these again. 1 plus 0.1 over 12 times the previous number, and then minus $213.59 like that. My A sub 1, of course, is 3,000. I'm just going to write it right below. So that's not what they wanted. They do want to figure out how long it takes to pay back the loan and what's the amount of the last payment. So if I did the spreadsheet again, I mean, this tab thing was fun, but I'm going to undo and find what we were doing before. This stuff. So let's do 3,000. Let's do 1 plus. I'm still to do the rounding thing that they're doing just to kind of keep it consistent. 1 plus 0.1 over 12 times the previous amount minus $213.59. Oh, missing parentheses somewhere around this guy. Okay, and then copy and paste that and see what's going on here for a few months. Okay, hits negative at some point. So after 15 months, I finish making payments because then it hits negatives, I suppose. Is that kind of how they ask it? It says the monthly payment. How long does it take to pay back the loan? I'm going to say 15 months. And then the amount of the last payment. Basically, on that last payment, I'm going to add an additional 1 cent to the value. Let's truncate this by a decimal. Give me a second. Truncate by decimal. So I'm going to add an additional 1 cent to that last payment to make it $213.60, I believe, on that one. So 15 months and $213.60 if I'm learning how this stuff works now, basically. So part A. Is there a part A? No. It'll take 15 months. And last payment equals 213.59 plus 0.01 equals 213. They really want that extra cent, yo. They really want that extra cent, yo. Number 66, how do you see it? The graph shows the first 6 terms of the sequence a sub 1 equals p, a sub n equals r times a sub n minus 1. Now, we haven't seen one of these together. I know one thing they're going to ask about. Common ratio is negative. And common ratio is less than 1. Well, I haven't seen the question, but I'll see what they say. Describe what happens to the values in the sequence as n increases. The values are getting closer to 0. The values are approaching 0. And they are alternating signs. I tend to say the word oscillating. They're alternating signs as they go. Part B, describe the set of possible values for R. Explain your reasoning. This is what I want to talk about. Your R values are number 1, diminishing, but number 2, changing signs. Therefore, your R value has to be something between -1 and 0. I don't know what it would be specifically, but this is why this happens. The reasoning is here. You're approaching 0, so your common ratio has to be a number less than 1. Between, a fraction. Between -1 and 1. It needs to be negative because of the oscillating signs. So that's what we're going to say for that one. Okay, number 67. The rule for a recursive sequence is as follows. Tell me, book. F of 1 is 3. F of 2 is 10. Oh, no. F of n is 4. Oh, 4 plus 2 times f of n minus 1 minus f of n minus 2. As long as I don't have to graph. Write the first 5 terms of the sequence. All right, we might have to write these ones out. So we have the first 2 terms. So that's cool. We only have to do it 3 more times. This was a 10, right? Okay, f of 3 is going to be 4 plus 2 times f of n minus 1. F of n minus 1 is not f of 1. It's the one right before it. So f of 2, which is 10, minus f of 2, which is 3. 4 plus 20 is 24, minus 3 is 21. F of 4 is going to be 4 plus 2 times 21 minus 10. That's 4 plus 42, which is 46, minus 10 is 36. And f of 5 is going to be 4 plus 2 times 36 minus 21. That's 4 plus 72, which is 76, minus 20 was 55. I was going to say, is this Fibonacci sequence? But I don't think it is. Because otherwise I'm like, we have a different way of writing it. Use finite differences to find a pattern. What type of relationship do the sequences show? Oh, hold on. Let's write this thing out. So 3, 10, 21, 36, 55. Okay. Use finite differences to find a pattern. So what? Plus 7, plus 14, plus 15. Wait, is that right? Plus 21. Is that what they mean? Okay. So the first differences are what? Use finite differences to find a pattern. Like the whole, do they have a common difference? Their difference is 7, their difference is 1, and their difference is 6. And this is minus 6, and this is minus 7. I don't know what they want on this one here. Use finite differences to find a pattern. Because I was hoping like, oh, it's not linear, but it's quadratic. No, it's not. It's cubic. No, it's not. 3, 10, 21, 36, 55. Yeah, I'm not seeing it. I'm not seeing the... Let me stew on this one. Hold on. Okay, you know what would really help? If I wasn't stupid. I put 10 plus 14 is 21. I saw this 7, and I was thinking 7 plus 14 is 21. Let's do that again. Time out. This is not plus 14. This is plus 11. Plus 11. And then I somehow did 36 plus 21 is 55. That was just wrong to begin with. I don't know what was going on. Obviously, my brain is mush. Okay, let's look at that all over again. I've tapped out. That is a common difference of 4 now. There's my finite difference thing. The second differences are constant. This is a quadratic. Okay. Super apologies on that, guys. I am checked out. I don't like that, but I am. Okay, now, this is part B. Use finite differences to find a pattern, etc. Write an explicit rule for the sequence. That's a different story because, I don't know. You have to come up with, well, it's a quadratic. You have to come up with some sort of thing, like some sort of a sub n equals. Now, if I did n squared, that would be wrong. You know what I mean? Because that's not it. I'm trying to think of like what the best ways are to do this as well. So this is like, I got to do something with 1 squared here. If I did 1 squared plus 2, that would give me 3. 2 squared plus 2 would not give me 10, right? If I did 2n squared plus 1, 2 times 1 squared plus 1, that would give me 3. 2 times 2 squared is 4, times 2 is 8, plus 1 is 9, not 10, but plus 2 would be 10. 2 times 3... Oh, does that work? Hold on a second. What if I do plus n? So, 2 times 1 squared plus 1 is 3. 2 times 2 squared plus 2 is 10. Oh, 2 times 3 squared plus 3. 9 doubled is 18, plus 3 is 21. Okay, I didn't check these other two. Just when I got that one, I got kind of excited. 16 times 32 is 36. Okay, I think this works. Oh, you can't see that. I don't know why I came up with that, though. I got to think about how to do those in general. 25 to 55. This works. All right, that's it. Now I can explain it. I discovered it. Okay, number 68. Making an argument. Your friend says it's impossible to write a recursive rule for a sequence that's neither arithmetic nor geometric. Is your friend correct? Justify your answer. Of course not. We did a bunch of these things. One is the Fibonacci sequence. Wrong. Incorrect. The Fibonacci sequence. There are a bunch that we've done. Is neither arithmetic nor geometric. Sometimes I don't know why they ask the question after we've done them rather than if they did it right before. They've done some where they set it up right before and then you use them for the problems. I don't know why they do it after because then I can say, see example this and this. All right, number 69, critical thinking. The first 4 triangular numbers t sub n and the first 4 square numbers s sub n are represented by the points in each diagram. So the triangular numbers, we got 1, 3, 6, 10. Square numbers, we got 1, 4, 9, 16. Write an explicit rule for each sequence. So triangular t sub n values, this isn't the equation, but the triangular numbers, we got 1, 3, 6, 10. So t sub n equals an explicit rule. Well, we got a plus 2, plus 3, plus 4. That's how the triangular numbers kind of work. But they have a constant difference of 1 that makes it a quadratic. So we're going to have to come up with another quadratic here, plus 1, plus 1. So this can be 1 squared. Great, I have to come up with these. 1 squared. Oh, I think I know it. So like this could be 1 squared minus 0, and this could be 2 squared minus 1, and 3 squared minus 2. Oh, that doesn't work. That's not 3 squared minus 2. Can I use the term before it? The other one's going to be easier to do. The square numbers are going to be easier to do here. I could do it if I made a system of 3. If I did a system of equations, I could probably come up with it in some sort of way. when I'm substituting, oh man, this is going to be tough. I don't know. So let's do this. When I'm substituting 1 into here for the ax squared plus bx plus c, ax squared, a times 1 squared plus b times 1 plus c equals 1. If I plug in 2, I'm getting 3. And when I plug in 3, I'm getting 6. So in rewriting that, that is a plus b plus c is 1. 4a plus 2b plus c is 3. And 9a plus 3b plus c is 6. Okay. Using elimination, I can eliminate c's by subtracting some things here. Pardon me, I'm going to be doing this mentally a lot. 4a minus a is 3a. 2b minus b is 1b. 1b. C minus c is 0, and 3 minus 1 is 2. And 9a minus a is 8a. 3b minus 1b is 2b. C minus c is 0, and 6 minus 1 is 5. If I multiply this by negative 2 here, I get negative 6a minus 2b is negative 4. If I add down these lists, I get 2a equals 1, so a is 1/2. In b, in terms of b, I'm going to use this one because it's an even number. 8 times 1/2 plus 2b is 5. 4 plus 2b is 5. 2b is 1, so b is also 1/2. Weird. A plus b plus c is 1. That's 1/2 plus 1/2 plus c is 1. Or 1 plus c is 1, or c equals 0. So my equation I can write is t sub n equals a, so 1/2 n squared plus b 1/2 times n plus c is 0. So this must be it. Let's see if that works. Substitute 1 in there. 1/2 plus 1/2 is 1. Plug in 2. That's half of 4, which is 2, plus half of 2, which is 1. 2 plus 1 is 3. Plug in 3. Half of 9 is 4.5, plus half of 3 is 1.5. 4.5 plus 1.5 is 6. Plug in 4. Half of 16 is 8, plus half of 2 is, or half of 4 is 2. 8 plus 2 is 10. Yes, that works. All right. S sub n, meanwhile, is that the terms are 1, 4, 9, 16, etc. That is S sub n equals n squared. Okay, I'm done with that one. Part B, write a recursive rule for each sequence. That actually might be easier for the first one. So for 1, 3, 6, 10, once again, 1, 3, 6, 10, write t sub n. This is, the first term is 1. The next term is, oh, geez, how do I say this? This is, well, you're adding 2. Oh, do we have to do the explicit within the recursive? You have a common difference that's increasing. So, oh, no, you can just add your term that you're doing. For the second term, you're adding 2. The third term, you're adding 3. So we can just say, let's do t. T sub 1 is 1. T sub n takes your previous term, and I think it just adds n to it. 1 plus the term, for the second term I'm adding 2, for the term I'm adding 3. So yeah, we're just doing that for this one. For S sub n having 1, 4, 9, 16, etc., we're not just adding n, we're adding the next odd number. So plus 3, plus 5, plus 7, they have a common difference of 2 each time, plus 2. So, you know, we did this in the past, and I need to recall it again. So it's like there's an arithmetic sequence within where, like, for the second term, the first term is 1. The second term is 1 plus n, I think it's like 2n minus 1. Like, it takes the first term, the second term takes the first term, obviously plus 3, but 3 represents more specifically in that second term, 2 times the second term minus 1. 2 times 2 is 4, minus 1 there. The third term takes the second term of 4 and it adds 5. 5 is 2 times 3 minus 1, like that. So when we write this one out, it's going to be s sub 1 equals 1 and s sub n equals the previous term plus 2n minus 1, where n represents that term thing that you do there. So it's kind of like an explicit rule that you write to make sense of what these things are that you're adding each time. They have a common difference of 2, and then it works out in that way. Whew. Part C. Write a rule for the square numbers in terms of the triangular numbers. Draw diagrams. Oh my goodness. Draw diagrams to explain why this rule is true. In terms of the triangular numbers. 1, 4, 9, 1, 3, 6, 10. Oh, 1 plus 3 is 4, 3 plus 6 is 9, 6 plus 10. Oh, the diagram, because they make triangles. Oh, so S sub n, so the value of, say, the second term. Wait, can I start with the first term? They're both 1, so I don't know if I can explain that as well. I think we have to write the first ones then. The first one is 1. The second one is 3. And any S sub n. So if I want to find the second term of the square numbers, do I have to say that S sub 1 is 1 as well? Is that weird? The second term would take the first term plus the second term of those. So it would do t sub n minus 1 plus t sub n. Like that. Given all the other stuff we have to say before, like that. I mean, I guess we have the triangular numbers, but that's just writing the rule. That's part C. It says, draw diagrams to explain why this rule is true. Well, you can imagine the triangular numbers are right here. Like for the fourth term, I have them here. Like that, you know, and we're adding those 4 plus these 3. Yeah, it works out for sure. I mean, it does, right? I have this, like this guy is right here in this diagram. Boom. It's not drawn well. Those 10 are right there, and these 3 are right there. I have to draw diagrams to explain why it's true. So I'm just going to copy and paste the things here. I'm really tapped out. I'm sorry. This is unprofessional. So for the second term, this is, for example, I'll just do this. This is t sub 1. And this is the 3 triangular numbers. I should draw it more like a triangle. T sub 1 and T sub 2. This is T sub 2 plus T sub 3. This is the story. T sub 3 plus T sub 4. All right. Congrats to anyone who's watching this part of the video. Number 70, critical thinking. Was this last one critical thinking? Yes, it was. Was it critical thinking as well? Yes, it was. Number 70, you are saving money for retirement. Yeah. You plan to withdraw $30,000 at the beginning of each year for 20 years after you retire. Based on the type of investment you are making, you can expect to earn an annual return of 8% on your savings after you retire. Oh, for 20 years after you retire. So you retire and then the annual return. Okay. Let A sub n be your balance n years after retiring. Write a recursive equation that shows how it's related to A sub 1. So it sounds like you have a first term of 30,000. Wait. No, you're withdrawing 30,000. Your first term, what's your first term? They don't really give you, oh, they just said based on a sub n minus 1. Okay, so they don't give you a first term. So write a recursive rule. A return of 8%. We're going to be able to add 8% each year after retirement, but we are going to withdraw 30,000 each year after retirement as well. I think that's my part A. Part B, solve the equation from part A for a sub n minus 1. Okay, so we're going to add 30,000. A sub n minus 1. Oh, hold on. Let's take that equation that we have there. A sub n plus 30,000 equals 1.08 times a sub n. Well, we divide by 1.08. Boom. So it's solved for. Find a sub 0, the minimum amount of money you should have in your account when you retire. Hint, let a sub 20 equals 0. It actually makes sense because, yeah, 20 years after you retire, we need to make sure that this goes to $0. Okay, so we need a sub 20 plus 30,000 over 1.08 equal a sub 19. Am I saying this right? And a sub 20 is 0. So a sub 19 is that. So we just have to roll backwards on this little bit. Do I go to a spreadsheet again for this? If I do, I'm going to go to the spreadsheet for this. Give me one moment. In my spreadsheet, I'm going to go backwards. Here's your 20, and we're going to do minus 1 each time. To find a sub 0. This is going to be a sub 20 is 0. This is going, I don't need this number. This is going to be the previous one plus 30,000 over 1.08. Copy paste till you're 0 or something like that. Okay. So that's when it goes down to 0. And we do the previous one each time. So a sub 0 should be $294,544.42. That's what I'm going with. All right. A sub 0 equals $2,904,544 and how many cents was it? And 42 cents. That's when we retired there. Solve the equation for that find a sub 0. All right, that's it. Guys, that'll do it for this one. This is Mr. Robinson. Thanks so much for watching. Giants won. I knew they were down 1-0. I didn't actually see the come from behind victory. I'm going to have to watch it at some point here. Yeah, we slowed down tremendously at the part that I anticipated that we would. We hit word problems around problem 50-something, 53. I don't know, maybe it was problem number 50 itself. But tremendous slowdown there. Me exploring some problems, me struggling with problems. This is going to happen, man. These ones here, especially when I tap out mentally, this is something where... Apologize for that if you stuck around with this stuff. In general, listen, the IM3 stuff got a little difficult at the end compared to the IM1 stuff for recursive rules. But in general, a lot of these things were covered in IM1 in such a way that almost that video can help you with recursive rules for arithmetic and geometric sequences. But guys, that's the end of the chapter. We are going to hit chapter review and chapter test stuff. They might hit some rigorous questions like this on section 7.5. We'll see how it goes. Thank you so much. Take care. I'm going to see you in the next one.